Okay, so last time we used this general form of gravitational potential energy in conservation of energy, solved some problems. Okay, conservation of energy is still the same. The law is still the same, right? It's just this term, we don't use mgh anymore. We use this new term, and then this r, remember, is always a distance from the center of this planet or star to where the object is. Okay, if you have the height, and then the r is usually the radius of the planet or star plus the height. And the last thing we discussed was this escape velocity or speed. Right. So we also used conservation of energy to derive that. Right. Remember what we did? Imagine this is the Earth. This is the initial point. I want to launch a spaceship, say, and my goal is to have it to travel really, really far away from the Earth. Then I set up conservation of energy, right? I still do delta K plus delta UG equals 0. And then if I wanted to go to really far away, that means the RF is going to be almost infinity. I want this RF to be almost infinity, right? You rearrange this equation, you will find the minimum speed required on the surface. At the surface of the Earth, it's going to be this equation, and we call it escape speed. That's going to be the minimum speed this object can escape from the gravity of Earth or any planet or star. Right? So this is going to be a general conclusion. You don't need to remember this conclusion. There are so many conclusions in this part. You just need to know how to derive that. Okay, everything comes from this and this. Right? These are the two. This is the fundamental theory we learned. This is just a general form for gravitational potential energy. Okay. Now what I want you to do is this. Let's just calculate the escape speed from the Earth. So that's lecture 19, slide 9. So all I need, right, if you want me to calculate the escape speed from a planet or star, just give me the mass and radius. Okay, so the mass of the radius, and the radius of the Earth, we have been using them many times. So plug these numbers in and find the escape speed for me from the Earth. Okay, do the math. All right, so if you plug numbers in very carefully, so for the Earth, the escape speed you can find, it's going to be 1.12 times 10 to the 4th meters per second. Well, it's definitely a very large speed. Like I can run, you can accelerate a person to that speed. Like you can run yourself to accelerate yourself to that speed. But we do have technology to accelerate a spaceship to that speed using the present technology. Okay. So that's why we can send spaceships. We can send detectors, to the moon, to Mars, to even outside the solar system. Okay. Now we can also calculate the escape speed for every planet, star, a planet and moon and sun in our solar system. So take a look at the table on slide 10. So these are the escape speeds calculated for these guys. Now we can use these escape speeds to explain some facts on the left. Okay, so for example, the moon and Mercury, they don't have any atmosphere. Why is that? Okay, take a look at the escape speed from the moon and the Mercury. The escape speed from the moon, 2.3 kilometers per second. Yeah, still very large, but it's the smallest in this table. The Mercury, okay, the second smallest. Okay, so the moon and the Mercury, they have the smallest escape speed in solar system. So that means it's easiest to escape from these two guys, right, the Moon and the Mercury, than other planets in the solar system, right, because they have the smallest escape speed. And then remember, these molecules in atmosphere, these molecules in atomic scale, they move really fast. It's very easy for them to reach this kind of speed. Okay, so the oxygen, nitrogen molecules, they move really fast. It's very easy for them to escape from the Moon and Mercury. So that's why the Moon and Mercury, they don't have a gravity strong enough to keep these molecules. Okay, it's very easy for these molecules to escape from that. So that's why they don't have an atmosphere, because the velocity, the escape velocity, is too small for these oxygen, nitrogen atmosphere, the molecules. And that also explains Mars has a very thin atmosphere. Take a look at the escape speed from Mars. That's 5 kilometers per second. Okay, it's a little bit larger than Mercury, but still very small. So that's why it can only keep, a very small amount of molecules. Okay, so that's why Mars has a very thin atmosphere. Okay, so Earth has a very thick atmosphere, and of course these gas giants, they also have very thick atmosphere. Okay, so we can also explain this using this experiment, the difference in the atmosphere, okay, on the Earth and on this Jupiter, Saturn, and all these gas giants. The difference is this. We know that the atmosphere on the Earth, okay, it's made of mostly oxygen and nitrogen. But the atmosphere on Jupiter, Saturn, and all these gas giants, it's made of mostly hydrogen and helium. Okay? And the abundance of hydrogen and helium in the universe is much, much larger than the oxygen and nitrogen. Okay? So it's very easy to find hydrogen and helium in the universe than oxygen and nitrogen. Okay? Because they are the lightest elements. Right? Then how come the Earth can only have oxygen and nitrogen, and then but the other planets, their atmosphere has hydrogen and helium? Because the Earth has you see that the escape speed we just found, okay, 11.2 kilometers per second. All the other gas giants, they have an escape speed larger than the Earth's escape speed, right? All of them are larger than it. So that means it's harder to escape from these gas giants. Right? It's easier compared to gas giant. It's easier to escape from the Earth. Okay. Now let's think about the hydrogen and helium. They are very light. Okay. So they can travel, and there are a lot of hydrogen and helium in the universe, but they can, compared to oxygen and nitrogen, if I ask you, hydrogen and helium, they travel on average, they will travel faster or slower than oxygen and nitrogen. What's your answer? They are lighter than oxygen and nitrogen. So on average, they could travel faster in the universe, right? You can throw this marker very easily. Can you throw this table? Well, that's really hard, right? So heavy objects, they, on average, in the universe, they would definitely travel slower than lighter objects, right? So hydrogen and helium, they are light. Even though there's a lot of hydrogen and helium, but it's easy for them to escape from the Earth, okay? Because Earth has a escape speed, but it's still too low to keep hydrogen and helium. That's why Earth can only keep oxygen and nitrogen, because oxygen and nitrogen, they are heavier, right? So they move slower. So Earth can keep oxygen and nitrogen, okay, which is a key to the development of life on Earth. Okay, and then, but the gas giants, they have a much greater escape speed. So even hydrogen and helium cannot escape from them. So it's very easy for these planets to keep hydrogen and helium. And hydrogen and helium, they're much more than oxygen and nitrogen in the universe. So that's why the atmosphere on these gas giants, it's mostly hydrogen and helium. But on the Earth, hydrogen and helium, it's very easy for them to escape from the Earth. So the Earth can only keep heavier molecules, oxygen and nitrogen. Okay, that's how we use the escape speed to explain these facts. Very interesting. Now I want you to do something else. Still escape speed. I'm going to give you a very special star, slide 11. Suppose a star has 4 solar masses, so it's very heavy. It's 4 times heavier as the Sun, but the radius is only 4 kilometers. Okay, so that means it's very small, right? 4 kilometers. That's very small. And then, so that means this star is very heavy but very small, so it's very dense. It's very dense. I want you to find the escape from this star. Okay, using the numbers. Okay, if I want to find the escape speed, all I need to do is just plug numbers into this equation, right? And it's going to be a constant for a specific planet or star. I just need the mass and radius. The mass is 4 times the mass of the Sun, which is given. The radius 4 kilometers. Plug them in. Find the escape speed for me. All right? Okay, if you have plugged all the numbers in carefully, you should find the right answer is B. Okay? So remember that the R you plug in is 4,000 meters. Okay, don't plug in 4. We have done that many times. Now, what's the problem? There's a problem with the speed, right? If you know speed of light, what is speed of light? Speed of light is this. And then speed of light, most people know that, right? Speed of light is the limit of a speed in this universe. Nothing can be faster than the speed of light, okay? And that's a conclusion from Einstein's relativity, okay? So far we don't have any evidence against that, okay? A lot of physicists they tried this, okay? They tried different kinds of experiments. They want to find if we can accelerate particles to faster than speed of light. No, all these experiments fail, okay? So that's why we have a very strong belief that this is true. This is a fundamental truth in this universe. Nothing can be faster than speed of light. Even if we meet some aliens in the future, even they have like, you know, some technology like a million years advanced than us, this is still true. They cannot overcome this limit, okay? Because Einstein's a genius, okay? Don't ever bet against Einstein. So that means that for this star, the escape speed is even greater than light. So that means nothing can escape from this star, right? Even light cannot reach that speed. So nothing, okay? Then if nothing can escape from the star, what is that? That's a black hole, okay? So black hole was a prediction made by physicists in the first place, okay? Yeah, it is weird, right? But it is a prediction from this theory. And if this solution exists, then nature knows that, then God knows that, right? So you should find these solutions exist in nature. True, this is a very extreme, this is a very special star, right? Very heavy, very dense. Normal stars are not gonna like that, right? Like the sun is not like that. But we're not talking about like 10 stars in this universe, right? We're talking about countless stars, okay? The base, excuse me, the base number is so large, okay? Even if this is an extreme case, very extreme, there got to be some stars like that in this huge universe, okay? So then physicists started to search for that, okay? And then they did find evidence for black holes in this universe. So it's not like, this is not a science fiction idea. A lot of people think this is a science fiction idea. No, it's a well-studied physics subject, okay? And if you know that Stephen Hawking did a very nice work on black holes. So, and then you see that it's not because like this scientist or this science fiction writer, they're like, oh, black holes are fun. let's just make something like a black hole and then write a science fiction about it. No, this idea first was predicted from this theory by physicists. Then they started to look for that because there's countless stars in this universe. And now we do have strong evidence of a supermassive black hole at the center of the Milky Way. Look at the slide on slide 12. That has a mass of 2-3 million solar masses. Wow, it's really heavy. It's very dense, right? Well, you can't see black holes, right? You can't detect the black holes directly, but you can detect the motion of the stars and planets around it, okay, to confirm the existence of a black hole. So pretty much for every galaxy, there's a very supermassive black hole at the center. That's why the galaxy, all these galaxies, they're rotating about the center. So they do need a centrifugal force. You see that? This theory, they're still true. They're even true in galaxies because they're fundamental theories. There must be something at the center pulling everything in this galaxy toward the center. So usually that's a very big black hole at the center for most galaxies, okay? So there is a supermassive black hole at the center of Milky Way, okay? So that's a black hole. That's a conclusion from this theory, right? It's very interesting, but it does exist. So we still don't know what's going on in a black hole. It's a very interesting topic. You pretty much have seen like science fiction movies on that, but we don't have anything inside black hole. We don't have any theory for that, right? Because that's like a singularity. Everything fails. All the laws we learn, all the laws we have fail inside black hole. So it's very interesting. We don't know what's going on inside black holes, but they exist in nature. Okay. So if you heard about it, slide 13, I'm going to tell you some interesting news in physics. In 2016, the LIGO experiment, they announced the first observation of gravitational waves. Okay, and that's the first time in human history we detected gravitational waves. And these gravitational waves, they were generated from a black hole merger about 1.3 billion light years from Earth. So these two black holes, they are rotating around each other. At the end, they get closer and closer, then they merge into one. So it's a big explosion, That's why we can detect the gravitational waves from this event, okay? Because gravitational waves are so weak. Who predicted the existence of gravitational waves? Again, it's Einstein. Einstein is a genius, okay? So that was a prediction from his general relativity. Okay, it's a prediction from his theory. So gravitational waves, it's pretty much like the waves we see every day, like water waves, EM waves. But gravitational waves are so weak because of this G constant. You can think of this as like characterizes the strength of the gravitational waves. It's so weak, so it's very hard to detect. Okay. So even Einstein thought that when he made the prediction, but he thought humans are never going to be able to detect the gravitational waves because it's too weak. Okay, I can give you an example, right? If you are sitting in this room, right, I lecture, you can hear me because your ears receive the sound waves, right, in the air. Okay. Okay, obvious. What if I lecture here? I want you to be at in the gym. Can you still hear me? You're gonna be like, no, there's no way I can hear because I am too far away from you, right? And then when your sound waves reach the gym, it's almost like zero. I can't hear anything. What if I tell you that I'm gonna lecture in China? I want you to hear in the USA. You will say, well, that's ridiculous. Why do you do that, right? Because I can't hear you. The waves are going to be too weak when it reaches me, right? The sound waves. And gravitational waves are even worse than that. Okay? So that's why Einstein thought that we are never going to be able to detect the gravitational waves, okay? But only after 100 years, we are able to detect the gravitational wave. So it's a big triumph of physics, science. Okay, and then this black hole, and it's from a explosion. So that's why these gravitational waves that they are showing now, right? Everyone, like we are also emitting gravitational waves, but they're just too weak. We can't detect that, right? This is a big event, a big explosion. So that's why the gravitational waves, they can be detected. But take a look at the number. That's 1.3 billion light years from Earth. That means, because light travels to 1.3 billion light years, that means it has taken light, the information at that point, 1.3 billion years to travel to Earth. So we have detected some signal from 1.3 billion years. Okay, this is something already happened 1.3 billion years ago. And then light has traveled, the gravitational waves, they have traveled 1.3 billion years to reach the Earth, and we have detected that. Isn't that amazing? Okay, physics is always amazing. Okay, it's just a lot of people don't know it. And this is also the first time human detected a binary black hole merger. Okay, so I attached a video, a link to a YouTube video. Okay, so the LIGO group, they explain this exciting discovery. Watch that video, it's very exciting. Okay, so that's black holes. So and then I'm going to tell you something else. So physics is very interesting. There are still a lot of ideas. They sound like science fiction idea, but they're actually topics people study in physics. Okay, so that's real. These things are real science. Black holes, they're real science. Okay, not science fiction ideas. Now I'm going to tell you something about dark matter and dark energy. So they're also interesting. They're very mysterious. They're even more mysterious than black holes. Well, I shouldn't say they're more mysterious, because black holes are also mysterious. So what is dark matter? I believe most people have heard about these two names. First of all, I want to make it clear, dark matter and dark energy are not related. They're two different things. The reason we call them dark matter and dark energy is because we know nothing about them. So they appear dark to us. Okay, we don't know anything about them. They're not related. Okay, dark energy is not the energy of dark matter. Okay, so maybe you're not going to remember everything I said in this class after this semester finishes, but I hope you still remember this. Okay, dark matter and dark energy, they're two different things. They're not related. Okay, it's just that they have the word dark in their name, but they have nothing to do with each other. What is dark matter? Okay, dark matter is this. First of all, so for example, take a look at our solar system, right? All these planets, they are orbiting the sun, right? The sun is really big at the center, so Mercury, Venus, Earth, Mars, right? Okay, all these planets, they're orbiting the sun. So they're like satellites, right? They're like if I want you to make a graph, plot the velocity of these planets versus the distance, you should get something like that, right? Because we drew that conclusion. So that means the orbiting velocity of these planets should go down with the distance, right? Remember, the r is the distance, right? If this is the sun, this is the distance for the Mercury and the Venus and the Earth. So you would actually get something like that, right? You should get, right? If I want to plot the V with r, right? So that means the far away from the sun, the smaller the rotational, the orbiting velocity becomes, because that's a theory, right? So take a look at the image on slide 14. So the red curve, it's gonna be your prediction, right? So it should go down as the distance goes up, right? When it's very, very far away from the center of any galaxy, right? But then, that's the prediction from all the theories we learned. That's the prediction. But then, when the physicists observe the universe, they don't get that. They get this white curve. Look at the white curve. So, looks like the orbital velocity of the planets or anything rotating about the center, almost the same. So almost a flat line. So how do you explain that, right? You can't explain that using that theory. It violates that theory, okay? So a solution some people proposed. So you have to answer these questions, right? This is a puzzle, okay? You have to fix that. So the solution some people propose is that there must be a lot of matter. So in the solar system, more than 90% of the mass is the sun. Okay, pretty much all the mass is here, right? So all the mass is here. Then of course the amp you plug in, then the velocity is gonna go down. So one solution to fix this is that they imagine there's a lot of matter, not just invisible, all around. Okay, so this matter all around the solar system, we can see them, but they have mass. If they have mass, they were going to provide a lot of them, not just like a little bit, a lot of them. They're going to provide more gravitational force for these planets, even far away, right? Because this guy's going to provide some force and also gravitational force. So that's going to add the centrifugal force. So at the end, even the planets very far away from the center, they get some strong centrifugal force. They can still rotate with almost the same speed as the planet the closest to the center. And then because we can't observe this matter, okay, we call it dark matter. So don't think it's silly. Don't think this is a ridiculous solution. Why do you propose something we can't see? I've showed you that the neutrino, the discovery of neutrino, right? Because we do experiments, and it seems like it always violates conservation of momentum. So one solution Pauli proposes that there must be something we didn't detect using our present technology, okay? Because we are stupid, okay? God is really smart. We are stupid, okay? So even though we have already made a lot of progress in finding the mysteries in the universe, but there's still a lot of things we don't know. Like dark matter is something we don't know, right? This is the solution people propose to solve this problem, but still, we still don't know if that's true. We still don't know what dark matter is. It has mass, it must have mass in order to solve this problem, but we can see that. We don't know anything around us that has that properties, so that's why it remains dark to us, okay? And then there are still a lot of people doing research on dark matter. So far, we still haven't solved this problem completely. This is still a hypothesis. Is this the right solution? No one knows. Okay, but that's how we progress in physics. Okay, so that's dark matter. So that's because you need to solve this problem, right? You need to explain the observational results. That's your observations, right? If your theory doesn't agree with the observations, you have to fix your theory. You have to modify your theory, right? Okay, so that's dark matter. Now, then what is dark energy? Dark energy is even more mysterious than dark matter, okay? Think about this, because Newton discovered that everything in this universe, they all have attractive force toward each other, right? So everything is attracting each other. Then if I ask you this question, so if everything in this universe is attracting each other, right, there's always attractive force between them. You would say the universe it's gonna tend to shrink or expand in size if everything in this universe attracts each other. What's your answer? Intuitively, it's just gonna it's gonna shrink, right? If then say the attractive force between me and everyone in this room is strong enough, I'm just gonna attract everyone toward me, right? So if anything in this universe is always has an attractive force on each other, then the size of a universe should be become smaller and smaller, right? In the long run. And then that's our prediction. Again, again, the nature never fails us, okay? When you observe the universe, now this is not what you see. You see the universe is expanding. And it's expanding faster and faster. It's expanding at an accelerating rate. So that's so ridiculous. It's getting bigger and bigger and with an accelerating rate. Again, how do you explain that? Okay, if your observations don't agree with the theory, you have to modify your theory. You have to find a solution. So one solution is this. Then some people propose that there must be some form of matter or energy, and then from Einstein's theory of general relativity, matter and energy, they're the same thing. So there's some energy form or matter form in this universe. They provide, it's very weird, they provide a repulsive force. So all these matter, they repel each other, like the positive and positive charge or negative and negative charge, okay? They repel each other, and the force, the repulsive force between them is so strong that's going to overcome the attractive force between all these stars, galaxies, all these things. So that's why the universe is expanding. Again, is this the right solution? We don't know. We're not sure. But this is one possible solution people proposed. And then there are still people working on that. A lot of people working on that. But we still don't know what dark energy is. We just know that if we want to fix this problem, one possible solution is that there might be some energy form all around us. So there's even dark matter in this room. You just can't feel that, okay? And that's not weird at all. There are millions of neutrinos coming from the sun, passing our body at every second. We don't feel them because they don't interact with these particles, okay? Dark energy, it's even more mysterious than that. It doesn't really interact with normal matter, so that's why we don't feel the existence of dark energy. But again, that's a possible solution, that's a hypothesis. Is this the right solution? We're not sure, okay? People are still working on that, trying to fix this problem, okay? And then, take a look at the last slide. If you do the math, and then you calculate the dark matter, the dark energy in this universe, and it turns out that the universe is made mostly dark energy, like 73% of the universe is made of dark energy. And another 23% of the universe is made by dark matter. You can do the math, right? Because you can use the expanding rate to calculate the required amount of dark energy. It turns out to be a lot. You can also use this observational curve to determine the required dark matter, and it turns out also be a lot. So the normal matter we know is going to be less than 5% of the universe. Okay, we only know less than 5% of a universe. Isn't that amazing? Okay, so that's why there are still people studying physics. There are still a lot of unsolved problems in physics. What we are learning in this class, that's theories people discovered hundreds of years ago. Okay, so that's why you feel it's not that exciting, boring. There are exciting topics in physics, but the problem is this. The math is usually a barrier for a lot of people, for general public. If you want to do this, and if you want to do research, you want to read about black holes, dark energy, dark matter, you don't even know what these papers are saying because you don't have the math skills, you don't have the math background to understand that, okay? So that's a big barrier for a lot of people in trying to understand the most exciting topics in physics. Okay, so physics is exciting, it is interesting, but it's just that for general public, the requirement with general public don't have the required math skills to understand them. Okay, so we only like normally people just have like know some algebra and most calculus. So that's why we study all these laws. Okay, they seem boring. Okay, not interesting. But again, I hope I have convinced you that physics is very interesting, very exciting. Okay, maybe you're not gonna become a physics major, but in the future, if you have a kid, encourage them. Okay, we still need a lot of people. You see that there are still a lot of unsolved problems in physics. Okay, we still need a lot of young people to get into this field. And then we don't know when we're gonna see the next Newton, the next Einstein. Okay. All right. So and these things I'm not gonna test on these things. I just want to tell you these exciting stories in physics. Okay. Now we have finished this part. We're gonna move on to the next topic. This is pretty much the last topic in this class. Okay. Oscillations and waves. Okay, so lecture 20. Take a look at lecture 20, slide 1. So we do see oscillations and waves every day in our life, right? Their behavior a little bit different than like one object. Usually, especially waves, right? It's not like one object moving. Usually, a lot of particles moving in a pattern. Okay, so that's why we want to spend some time studying that. Okay, so we have already finished the gravity. Now, oscillation. That's easy to see, right? For example, the easiest one is this, right? If you have a spring, you attach an object to the spring, you just pull it down, let it go, it's gonna start to oscillate. Okay, so that's oscillation. And oscillation is something moving back and forth about an equilibrium position, right? And also the pendulum. If you make a pendulum is also an oscillating object, right? You pull it to one side, let it go, it's going to oscillate back and forth about the center, right? So oscillations very common in real life, and they always repeat this movement, right? They always repeat this movement. If there's no like friction, they will continue forever. And then oscillation usually has like at least two forms of energy involved, right? For example, the pendulum. So it's kinetic energy, potential energy, they're being converted to each other all the time. And the spring oscillator, it has potential energy, kinetic energy, and elastic energy involved, right? So oscillation usually has at least two forms of energy involved. Okay. Now, if something oscillating, it's repeating this movement, then you can also define a thing called period, right? Like what we did before with a circular motion. A circular motion, something is also repeating its movement, right? It comes back to its original point and then start another circle. So, and then the period, you can also define the period as one full cycle when something is oscillating this way or that way. When it starts from one position and then goes back and forth and come back to its original point, that time we call it period, right? So, and then we define this thing called a frequency, which is the inverse of the period. And this part, okay? So you can use this to describe how fast this thing is oscillating, right? If something has a very large frequency, that means it's oscillating really, really fast, okay? And the SI unit for this guy is going to be 1/2. And we do have a name for it. We call it hertz, okay? And hertz is just a new name for 1/2, okay? And then another thing we usually define in this part is the amplitude, okay? Because when something is oscillating, there's a maximum displacement it can go, right? Imagine this oscillator up and down. There's always a maximum displacement go. And also if you have a pendulum, you let it go back and forth. And this is going to be the maximum displacement it can go, right? So we call it amplitude, okay? I hope these names are very easy to understand. And then we're gonna just study the simplest oscillations, harmonic oscillators, okay? Again, don't be afraid of these fancy names. What is a harmonic oscillator? A harmonic oscillator is an oscillator where the restoring force is always proportional to the displacement of the displacement from the equilibrium, okay? So if you write it in a mathematical form as this, the restoring force is always going to be proportional to the displacement. And then the period doesn't depend on the amplitude. And this is a very interesting property of an oscillator, harmonic oscillator. We're going to see why the period doesn't depend on that, okay? And a pendulum is a harmonic oscillator because the force is always going to be proportional to displacement. And then anything attached to a spring, right? Because we know that the spring has a force. The force in the spring is always going to be negative k delta x. So this is already proportional to the displacement. So anything, if you attach anything with the spring and make it oscillate, it's definitely a harmonic oscillator, right? So you see that anything that obeys Hooke's law is going to be a harmonic oscillator, because that's a definition of harmonic oscillator. If the restoring force in this object, it's always going to be proportional to the displacement, that is a harmonic oscillator. Okay, that's just a definition. Okay, so and then I'm going to stop here for this video. We're going to continue the discussion on harmonic oscillators next time.